Vectors and scalars, or in other words, values that have direction and those that don't. A vector is a fancy name for a value that has a direction. This is Jack. This is Bob. And those are my drawings, and don't judge me. They are 6 feet apart, and the distance that separates them is not a vector. In fact, it makes no difference how they are arranged or how you view them, they are still 6 feet apart. Okay? So, no matter where they go, whether you're looking from one side or the other, or they are turned around, as long as they're 6 feet apart, the distance that separates them is 6 feet. So therefore, distance is not a vector. But, if we said that Bob is 6 feet to the right of Jack, now we have defined a vector known as displacement. And if you look at this graphic here, displacement is simply the straight line distance between the starting point and the ending point. You can follow this long, twisted, convoluted path, but in the end, displacement is your change in position from the start to the finish. Now, my convoluted definition is displacement is the straight line distance between the starting and end point with a reference to the direction from the point of view of the finish point. That makes total sense to me, but it might be confusing to you, and it probably is because I made this definition up, and you can probably find better ones if you look them up. But it makes sense to me. But let's try to look at it from another direction, and let's think of it like a number line. Okay, so to understand displacement, we need a reference point, a zero if you will, and think of zero on the number line. We have all the negative numbers getting bigger to the left, and we have all the positive numbers getting bigger to the right. And if we put a green dot there on the 5, we can say that the green dot is either 5 units to the right of 0, it is positive 5 units, or 5 units in the positive direction. Really what we're saying is, relative to the 0, which is our reference point, the green dot is 5 units away from it in the positive direction, or to the right. In any scenario, we define our starting point and look at what happens relative to that starting point. So in this example, the green dot has a displacement of plus 5 units, or it has a displacement of 5 units to the right of 0. In other words, we are saying the green dot traveled from the 0 to the 5. That's really what displacement means. It changed its position from 0 to the 5, and therefore the displacement is positive 5. So we say it has a displacement of positive 5, or the displacement is 5 units to the right of 0. And if that doesn't make sense, I want to discuss that 5 units to the right of 0 is a bit awkward. I only put that in there so that it can help illustrate the fact that vectors do require a direction. In actuality, the positive or negative sign is going to determine the direction of a vector more often than not. Plus 5 units implies that the vector points one way, whereas if we wrote negative 5 units, it would be pointing completely the other way, 180 degrees in the other direction. But what if I'm on a diagonal? Well, I'm glad you asked, but unfortunately, that's beyond the scope of this particular slideshow, which is one-dimensional kinematics. We will definitely get into diagonals and how we would treat them in the two-dimensional section. But for now, I'm glad you asked, but it's not part of this slideshow. So it is important, though, that we now talk about the convention of direction so that we can explain what we mean in one-dimensional kinematics. When we have a vector that points to the right or we have a vector that points up, we say that that vector is positive. On the other hand, if we have a vector pointing to the left or if it's pointing down, we define that as negative. So right now, if you remember your Cartesian coordinate system, we have the positive x direction and the positive y direction are the blue vectors there, or the blue arrows, and then negative x and negative y are the green arrows there. Simple, simple, right? So to recap vector introduction, a vector is a quantity that has a direction. The first vector we learned is called displacement, and it is the straight line distance between 2 points with a direction that references the starting point. In physics, you will often hear of displacement as a change in position. Vectors are often denoted with an arrow overhead like so. This isn't actually a recap, this is new, but it seemed like a good place to put it. Now, S with an arrow overhead means that that is a vector. S with an arrow overhead is the standard way you would handwrite a vector. In this case, we're talking about vector S, and S is often used as the variable for displacement. So back to our number line, here we have a dot on the 5, right? When we are talking about displacement, though, we are talking about a change in position. So we are talking about going from 0 to 5. So what we're going to do is get rid of this dot, and we're going to replace it with an arrow that starts at the 0 and ends at the 5. So the tail of the arrow is our starting point. The head, the pointy part of the arrow, is going to be at the finishing point. And that's how we would draw a vector. The length of the arrow is called the vector's magnitude. In this case, that is 5 units. The direction of the vector is given by positive or negative. In this case, it's positive. So S with the arrow is actually going to equal positive 5 units, because S with an arrow means a vector with the magnitude, the length of the vector, equaling the absolute value of the vector. Because the vector could point negative, in which case it would be a negative number. However, the magnitude will always be positive, and that's why you take the absolute value of it. By saying that vector S equals plus 5 units, we know the magnitude and the direction of the vector. Now, scalar. Scalar has nothing to do with scales. In fact, scalars are simply values with no direction. In other words, they are directionless vectors. Or even simpler than that, they are just magnitudes or quantities. And no, I'm not kidding. That's all there is to it. In fact, here are some common scalars. Mass, distance, speed, time, volume, temperature, area. These are all scalars, and I'm sure you know what all of these are. But some of these scalars have vector alter egos. Mass, for example. You know what mass is, or do you? Most of you think of it as weight. However, mass and weight are not the same thing. You will still have mass were you in space, and yet you would be weightless. Why is that? We will find out, but it has to do with the fact that weight is a vector, whereas mass is a scalar. Distance. We already know that the vector analog for distance is displacement. Soon we will learn speed, and its vector version is going to be velocity. And a very good introduction for that is this video by They Might Be Giants from their Here Comes Science album. This is Speed and Velocity. I urge you to watch the video.